Okay, so welcome to CS520, Theory of Programming Languages. And then this is a graduate level course on programming languages. And then I don't know how many of you have read this syllabus of this course or not, but this course is not about introducing, going through lots of different languages and then talking about their features and so on. The course is more about analyzing theoretical principles behind many programming languages. So the course is going to be very mathematical and also involve lots of symbols. Okay. And so the two main questions that we're gonna ask throughout the course is the following. Well, actually not two, one main question, which is how to analyze existing programming languages formally. So by existing programming languages, I mean programming construct. Some programming language has while loops, and some languages have support higher order functions. Sometimes some languages support continuation and so on, which is generalized version of GoTo. And some languages have type systems, some languages do not. Then there are many implementation techniques, especially for higher order languages, something called continuation passing style transformation and so on. So what we want to do is we want to look at these features, and then we want to come up with a mathematical description about these features so that we can prove some properties about this. So throughout the course, there is a big emphasis on mathematics. We are not, this is not a mathematics course, so we are not trying to prove proving non-trivial theorem is not really the main goal of this course. The goal of the course is more about learning mathematical tools to analyze highly complicated situations. But the tools that we are learning is going to be quite advanced sometimes. Okay. So let me give you some overview about some of the things that we're going to cover in the course. The first thing, So the first thing that we're going to look at is an abstract syntax. Okay, so the abstract syntax asks a very basic question, which is what is a program and what kind of syntactic object is it? There's an obvious answer to this question, which is you can say the programs are nothing but sequences of characters. And this is not a good answer. That's because program has a lot of interesting structure, and viewing programs as sequences of characters ignore all these structures, which turn out to be, which can be exploited. So instead, our appropriate answer to this question is initial algebra. So it's an instance of, we're going to use the two terms. One is computer science friendly. We'll say the syntax of a program is an instance of an so-called abstract syntax. Or mathematically, we're going to view this as an element of something called initial algebra, which appears, which is invented in the work on algebra and especially universal algebra. And once you view programs or syntactic representations of a program as an element of an initial algebra, then we can have some tools, like we can do syntax directive definition. And also we can have some principle that looks a bit like an induction, which is sometimes called structural induction. And these are the tools that we're going to exploit to study various programming languages. So the first, one concept that we're going to study quite a bit is the idea of syntax as an abstract syntax or as initial algebra of some signature. Because another big topic throughout the course is going to be a domain theory. So, and then to understand, one way to understand domain theory is to think about the functions that you see on the screen. So I define a Python function, capital F of G, which doesn't do anything. It just takes an argument G and returns G. Okay. Then we may ask the following question, which is, what kind of mathematical object is for capital F denotes? And there is an obvious answer. The answer is It's going to be an identity because it just return its input. It's just going to be on the identity function over some set or something D. But so this looks like a reasonable choice. But then things becomes complicated because in programming language like Python, you can apply function f to itself. Okay, so what you can do is you can apply function f to itself. So then it returns, if it doesn't raise any error, it just returns something. So, I mean, in terms of actual implementation, what happens is that the argument capital F is going to be an object, a function object, and then so we are passing function object as an argument to capital F, because capital F is the identity function. It's gonna just return this function object as the result. Okay, but from the mathematical point of view, this is, is not, causes some issue because we said this function F, capital F is the identity function over D, but D should, because D can take function F, the function F can take function F itself as a parameter. D should now include this function space itself. Okay, so you can see that, because we are passing this argument F as an argument, which means that the space where capital F lives should be included as the input domain of capital F. So we should have this type of property, input function space DROD. Okay, so and then right, but then this kind of property is not possible. So if we want to come up with some set D which have this property or some cousin of this property, and the set D is non-trivial in the sense that set D contains more than one element, then you can show that this is not possible. So there is no set that satisfies this property. And this is related to so-called Russell's paradox that you may heard of before. So we are in a very strange situation where we can write program and we try to understand the behavior of program like capital F that you see on the screen using mathematical ideas, what you learn in mathematics. But there is a mismatch. There is a program that we can write. On the other hand, the mathematical space that we are familiar with cannot accommodate the kind of function that we can write there. So what should we do? And the domain theory provides an answer about this. Okay, so later we will learn something called the domain, which is a set together with some extra structure. And then one thing that we will show is that if we assume that this function space D arrow D is not just arbitrary functions from D to D, but so-called continuous function. It satisfies some extra properties that are coming from the domain structure of the D. So then, we don't really have this problem. Okay. So what that means is there can be a domain D, which in a sense includes all the continuous functions from D to D. So if we have continuous functions, then all the continuous functions from D to D can be included in the domain D. I said this is not possible in a set. But if we impose some structure on D and then consider only continuous functions, then this will become possible. So what that actually means is domain theory is some abstract way of characterizing what kind of functions that you can write in programming languages. So it's not just talking about arbitrary functions. You pick specific kind of functions that, in a sense, can be implemented. And once you do this a proper mathematical formalization of what kind of functions you can write, then the problem that I talk about, which is function space, should be included into the input space, is no longer there. We can solve that problem. So that's the second big topic that we're gonna study. And the third one is gonna be the evaluation order. Now consider the program that you see on the screen, the small f that take x, it's a Python program, and just return, the x plus x as the result. Okay. Now consider the function application f, but its argument is another function application f of 3. So then we may ask the following question. This argument f of 3 is going to be evaluated before applying the outermost function f. So are we going to, so we have two functions, one function application, one for the outermost, second, the innermost. So then we may ask the following question, the function application of 1 happens before 2, or function application 2 happens before 1. Okay. In Python, 2 happens before 1, but that's not always the case in all the programming languages. Okay. There are some programming languages like Python or OCaml, Scheme, and so on, which support so-called eager evaluation, implement eager evaluation, where evaluation of the inner function call happens before the application of the outer function call. But there is also a programming language that implements so-called normal order evaluation, or sometimes called lazy evaluation, like Haskell. And in Haskell, the function application 1 happens before function application 2. And some languages like Scala has a mechanism to define a function that by default, all the functions in Scala implement eager evaluation, but there's a mechanism that you can define a normal order evaluation. The function that can be evaluated, that's evaluated according to the normal order evaluation. So we will study these two evaluation order. And then, right. So if you do this normal order evaluation, you might say, why do you want to do this normal order evaluation? One answer is, theoretically, it's quite efficient. In practice, it's not always, but theoretically, it's quite efficient. One way to see this is the following example. If you change the definition of function f so that it's a constant function, it doesn't look at its argument at all. Normal order evaluation, there is going to be only one function called because it doesn't evaluate its parameter, the f of 3. But if you do the eager evaluation, this function call happens twice. Okay, the function call happens twice in this example. So in theory, it's more efficient. In practice, it's not always, but in theory, it's more efficient. And furthermore, I think more importantly, this normal order evaluation has very nice mathematical properties. So doing formal proofs with Haskell is in some sense becomes a lot easier than doing formal proofs with either Python or OCaml Scheme, because of this evaluation order. So we will study this evaluation order using so-called operational semantics and denotational semantics and try to understand the consequences. We try to formalize this evaluation order rigorously using mathematical tools, also try to understand the consequences of these different evaluation orders. And there's one topic which we are not going to cover, but that's closely related to the topics that we are studying. And in fact, there's a chapter on type system in the main textbook that we are following. That chapter comes almost right after the part that we finish in the course. So in some sense, we are going to prepare you to study some theoretical analysis of so-called type system. So perhaps all of you have some experience with the types. I'm using using a mechanism or library that allows us to annotate Python functions with types. So, and in some programming languages like OCaml, you have to use, by default, you are always using types. And using types are very useful. It's really helpful because, if a programming language supports a very strong type system, just writing program that type check, that do not have type error, often once you do this, then your program very likely to be, to be correct. So just making sure your program type checked amounts to ensuring the correctness of your program. Okay, so it makes it much easier to develop correct program. But then there are two things that so ideally we want most of the programming languages to have types, but there are programming languages that do not, include the type. That's because there is, sometimes programmers have to write type annotation, and some programmers hate it. So ideally, we would like to have a programming language that infer types automatically. And sometimes it's possible, sometimes it's not. And then the study about type system in programming languages provide an answer for this question. And in fact, for some type system, about some which is implemented for OCaml, type inference is possible. And some programming languages like Python, if we want to implement automated type inference, then that's going to be much more difficult. And furthermore, once your programming language have types, and we can ask, you might say it's a bit philosophical, or but it's more rigorous. This theoretical question, which is what types actually means. Good answer for this is actually very useful. That's because once you have a good mathematical modeling or mathematical formalization of types, that can help you to prove correctness. That your type system always guarantees something. Also, it also opens the door of doing compiler optimization for well-typed programs. And the textbook explains types as a partial equivalence relations. Okay. So we are not going to cover this, but these are the kind of topics that are in line with what we're going to cover throughout the course. Okay. So let me list all the topics that we will cover throughout the course. So these are the, I think 1, 2, 3, 4, 5, 6, 7, 8. We're gonna cover 4, 7, 7 chapters from Raynor's book, and then 2 additional chapters from Tennant's book. And then before the midterm exam, the course will focus mostly on the features from imperative programming languages. So we will, as a warm-up, we're gonna study predicate logic. And then this studying predicate logic kind of introduce you to the idea of abstract syntax, syntax-directed definitions, and structural induction, and so on. Some key tools that we're gonna use over and over again when we study programming languages formally. And after that, we will study simple imperative language and a bit of a domain theory that allows you to give a formal semantics about this, and also some proof rules that will help you to write specification of programs in this language and prove your programs actually satisfy those specifications. And then we'll also study some advanced stuff like how to model continuations and other features in the programming languages, and also basic tools of operational semantics. After the midterm exam, the course shifts the gear and focus more on the high-order languages. So we will study the lambda. High-order language means it's a programming language that allows you to pass functions as a parameter to another function. Also return functions as a result of function calls. So functions becomes first-order objects in these languages. So we will study lambda calculus, and then we will study, we will look a little bit about eager evaluation and normal order evaluation. And then we will study programming language based on the eager evaluation and some extra feature called continuation in that language. But to study these languages formally, we need some mathematical tools. So the intervening chapters or intervening lectures will be about some mathematical tools, which will be a category theory. So we will use 2 chapters from Tennant's book on programming languages. They have an introduction to some gentle introduction to a category theory. And also the reason we study category theory is to show so-called existence of recursively defined domains. And so we will study go a bit deeper into the category theory that allows us to prove existence of recursively defined domains. And these tools that we develop are going to be used when we study these functional languages later. So, okay, so that's the quick overview about the course. And then the most of the information about the course will be available in the course webpage, which I set up in the GitHub. And then also the discussions and many announcements will also happens in the KLMS. So I strongly encourage, if you decide to follow this course until the end, I strongly encourage you to check the course webpage and the KLMS regularly. And one thing I noticed in the KLMS is that they changed the interface recently. So, I mean, just explore KLMS a little bit. I mean, now you can't really see the announcements in the list of the items. I mean, the written items. You have to click the right buttons to see the announcement and so on. So do some exploration that will help you to, I mean, not miss any of the important announcements. And then one very important things about this course is how we're gonna run it. So we will run this course in the style of not exactly Azure 4.0, but we will do it as a baby version of Azure, this EDU 4.0. Okay, so what that means is all the this real-time Zoom session, except this one, real-time Zoom sessions will be mostly about about the interaction between you and me, or maybe I can help you to deepen your understanding about what's really going on. And then the learning, the materials of the course will have to be done by you. And then I will provide the pre-recorded video lectures from the last year. They are all available from the course web. I mean, they're all stored in the YouTube. The links to those recorded lectures will be available, will be found in the course webpage. And also which videos to watch in each week is also indicated in the course webpage. So if you go to the course webpage, each week I say, okay, please watch these videos. And then if you click this video items there, then you will be directed to the appropriate YouTube video files. Okay. And then real-time Zoom sessions will be mostly done by question and answer sessions. They will happen on Wednesday. And what I will do is that, I mean, already for at each of these Zoom Q&A session, I wrote a posting in the Q&A board of KLMS. So if you go to the Q&A board of KLMS, I mean, I wrote some posting, and that posting say, for instance, I mean, maybe the next Wednesday next week, I mean, if you have any questions, please write it as replies to this posting. So I wrote a bunch of postings in the KLMS Q&A board. So if you have any questions, please write them as replies to these postings. And what I will do is I will look at the replies, what the questions written in the KLMS, and then based on the questions, I will decide which questions I want to discuss in these Q&A sessions, and then that's how I'm gonna run these Q&A sessions. And another important bit is there will be 4 oral tests. So in these oral tests constitute a significant part of the total marks of this course. So there will be 4 oral tests. I mean, you can see the dates on the screen. And then 2 of them will be scheduled during the midterm period and the final exam period, and 2 of them during the the outside of these exam times. And evaluations will be based on the 3 main things. There will be 4 homework problem sheets that will account for the 40% of the total marks. And Zoom oral tests will account for the 30%. And there will be two critical reviews, two critical surveys that will account for the 30%. So let me explain about this Zoom oral test. These are going to be the randomized in-class oral test. So you attend these oral tests maybe during the outside of the exam period. The tests go from 1 p.m. to 2:15. During the exam periods, it's going to go from 1 p.m. to 2:30. And I randomly pick students, and then I will ask questions to those students. And if the students answer question well, then she or he will get a mark, the extra mark. If she or he doesn't really answer the question well, then the students will get some deduction. And then if the students doesn't really attend this test at all, then they will get 0 marks. So about the 7.5% of the total marks will be allocated. So having 0 will have some significant impact on your final grade. And we are not going to do the attendance check for the Q&A sessions. My intention for Q&A sessions is really to help you understand what's really going on, and also sometimes help you to get an idea about how to approach homework problems and so on. So we are not going to do the attendance check, but for this Zoom oral test, we will do the attendance check at 1:30. But it's a bit weird kind of attendance check. That's because if a student get called before 1:30, so if a student get asked a question before 1:30, but the student is absent, then the student is regarded as missing the test entirely. Okay. So if you feel like, oh, you are lucky, then you can come at 1:30. Maybe you are lucky, so you will not get caught. But otherwise, you might get caught. Okay, so you can make a decisions about, attending these tests. And we are expecting you to answer questions over the microphone. So you don't have to prepare a microphone and camera for any of the other sessions. But for these 4 oral test sessions, be prepared. So make sure that you can access microphone. You can use microphone. Your microphone works okay. And then also make sure that you have a camera, video camera. So we may ask you to turn on your video camera, maybe during the attendance check, or maybe when I ask you a question. And the course webpage has a bit of more information. The final bit is that all the questions will be asked in English. If you feel more comfortable, you can answer them in Korean. That's not a problem at all. Okay. And then there will be 2 critical surveys. And then these critical surveys are about study an assigned topic for yourself and write a short review about it. But ideally, I want you to go beyond the simple surveys, simply summarizing what you looked at. That's okay, but ideally, I want you to do more than this. So in the course webpage, for instance, for the first topic, I pose a bunch of questions. This is exactly the same topic that I put the first one, the same topic that I put last year. Then the impression I got is that some students organize their surveys as a series of answers to all these questions. You don't have to answer all these questions. These questions are there to help you understand what's really going on. So you can do it that way, but ideally, I want you to think for your own, and then coming up with your critical view about particular topic. Writing, we will allocate 20% of the 20% for the writing, 40% for understanding, and 40% for the originality. The first critical survey, the deadline is April 28th, and the submission box, I created the submission box for this critical survey. So if you finish early, you can submit anytime. And then the topic is a concurrent separation logic. So this is the program logic, or you can say it's a formal system that allows you to prove the correctness of concurrent imperative program. And concurrent separation logic has been very successful. And then the inventor of concurrent separation logic received Gödel Prize. So Peter Hearn and Steve Brooks, they received Gödel Prize, which is not exactly Turing Award, but it's one of the prestigious prize for theoretical computer scientists. The second critical survey is a deadline is June 7th. So I think 1 or 2 weeks before the final exam. And it's a bit more open-ended. So I will ask you to pick one paper in these either POPL 19 or POPL 20 or POPL 21 or PLDI 19 and PLDI 20 and write a critical survey about the topic and of the paper. Okay, but the POPL and PLDI are the main programming language conferences. So and then papers there are typically quite hard, and I don't expect you to understand the topic of that paper very easily. So understanding that paper will require some further study. You can look at related work sections in that paper to go a bit deeper. And then, so what I want you to do is, I want you to understand specific problems that were specific research topics that's attacked by the paper. And then maybe you can provide some nice survey about the topic, and then you can position the paper in the context of kind of many research works done on that topic. And if you look at the course webpage, I will provide a very simple guideline for this second critical survey. Okay. So throughout the course, we will adopt a very strict policy for handling the violation of the honor code. So honor code means do not cheat. Okay. But cheating, especially now you are the graduate students, you have to be extremely careful about so-called plagiarism. Okay. And I'm sure most of you already are aware of you shouldn't do so-called dishonest academic behavior like the copying answers from your friends or maybe copying answers from some other sources from the internet. You shouldn't do this. But there is also another very important bit, which is don't make sure that you do not violate plagiarism. Do not fall into this plagiarism case. So if you copy a text from either papers or textbooks, you have to always rephrase them and also make sure that the source, point out the source of those texts. So there was a case last year. Students violated this honor code, and the students got F. So make sure that you are not really, you follow or respect this honor code. So this is the final slide of today. So this is some short information about teaching step. So I'm Hong Seok Yang, so I'm gonna teach the course. And there are two TAs, Sang-ho Lim and Dong-woo Woo. And so these teachings, and my office hour is from 6 to 7 p.m. on Monday. I didn't write the dates. 6 to 7 p.m. on Monday at Zoom. And so you can find the information about my office hours in the course webpage. I think you will soon find information about office hours of the TAs in the course webpage. And during the office hour, you can ask any questions about the course. So, and this is an hour for you. So try to exploit these my office hours. And that's pretty much everything I want to talk about today. So I will stay here maybe 10 more minutes. And so if you have any questions, ask me. Okay. So that's it for today. So thank you very much.